Okay. Okay, so the room's already kind of packed. I think it's time to get going. Hello, everyone. Thank you for being here. My name is Miguel. I'm a software engineer at a company called OutSystems, where I work in the artificial intelligence team. And for those of you that don't know OutSystems, we essentially build a development platform that's all about speed. So our message is about development speed, developing faster. And at the artificial intelligence team, we have this idea that faster development can be achieved by smarter development. And what do I mean by smarter development? I mean self-driving applied to development. So I don't want to tell the computer how to get to the place. I just want to tell the computer where I want to get, and I want the app to build itself. So that's the vision, and it might sound a bit like science fiction, but it's not really science fiction. It's already here. In fact, if you look, for instance, to Microsoft Excel, which is a fairly common application, it's installed in millions of computers. Nowadays, they have a part of this. So there are some data transformations that you can do without specifying the process that transforms the data. You just specify a few examples. How is the source data? How do you want the data to be transformed? And Excel automatically infers what's your intent. It understands what you want to do, and like by magic, it applies that transformation. So you're not describing the process, you're describing just the destination, and the computer does that for you. So we have this nowadays. It's getting there. Okay, so why graph neural networks? Well, what we found out throughout this journey is that graph neural networks is an awesome tool to have in our tool set when we're dealing with processing computer codes and with understanding code, generating code, fixing bugs automatically. This is a really great tool to have. And that's why I want to talk about this topic today. Now, to talk about graph neural networks, I should first introduce the topic of neural networks. So just for a quick check from the audience, how many of you have already used neural networks before? Okay, so a few of you haven't used neural networks. I mean, everybody has used neural networks. If you used a phone with predictive writing on the keyboard, you've used neural networks. If you used Google, you've used neural networks. So neural networks are nowadays used in lots of software. But of course, building them is a whole different story. Sometimes it's a scary story, so if we search for what's neural networks, what's this neural networks thing, all we see is like these images of brains and circuits and blue stuff and robots and the AI apocalypse. But neural networks are actually something simpler. They can be described in simple terms, so that's what I'm going to try to do now, going like from scratch to graph neural networks in under 40 minutes. Okay, so let's start with a very basic concept, which is the concept of a function. Function is something that takes an input and produces some sort of output. And all software can be described in terms of functions. The input can come from a keyboard, it can come from a file on disk, the output can go onto the screen, or some upload, anything. All software can be described in terms of functions and function composition. Now, what happens with machine learning is kind of the opposite of this. Instead of having a function that produces outputs, we have outputs and we infer the function from it. Okay, so we have inputs, we know how we want to transform that thing, how we want to classify that thing, and we ask the machine to get the function that does this for us. Okay? So this is the big difference between traditional development and machine learning. And doing this the machine learning way is often more complicated. You have to have the inputs, the outputs, you have to have a training process. So the question is, why would we want to do this the hard way? Well, if your problem is simple, you don't want to do it the hard way. So if you're building a function that just picks a number and returns the double of that number, it's so easy to specify that you'd never use machine learning for this. But if your problem is hard to specify, for instance, let's build a function that distinguishes between pictures of dogs and cats. This is really hard to explain, even for a human. If you're explaining to a child what's the difference between a dog and a cat, what are you going to say? They both have eyes, ears, nose, fur, tails. So it's difficult to describe the actual difference. It's much, much easier to show examples and say, see this image, this is a dog. See this other image, this is a cat. And let the child understand the difference just by looking into examples. So we humans work a lot like this. We look at the examples. We don't really know why, but we can understand something that tells these things apart. And that's also where machine learning is really powerful. So when we have these sets of problems that are really hard to describe, like image classification or identifying financial transactions that are fraud or legit, predicting stock prices, doing things on text interpretation like summarization, translation, all these problems are really difficult to specify by rules. And so it's very useful to use machine learning to solve these. And there's like an infinity of use cases for machine learning and for AI in software. OK, so let's learn functions. I mean, learning functions is actually a very hard problem. If learning any function was easy, we would just ask the machine, hey, learn me a function that makes me rich. The machine would learn that function, then you would run it and become rich. So no one's doing this. That must mean that making arbitrary functions is rather difficult. So we have to start by simplifying this problem. And to simplify it, we'll start by looking at the most basic kind of functions, which are linear functions. So if you see data that's following this kind of pattern, you see that it's a linear pattern, and it's kind of easy to predict even what the next elements here would be. The thing with linear functions is that they can all be reduced to a very simple format. So it's essentially multiplying by a weight and adding a bias. And all linear functions can be reduced to this formula. So this helps us a lot because now our problem is not finding an arbitrary function, it's just finding two numbers, which is w and b. And any student that has reached university knows how to do this with a system of equations to find the two variables. However, equations would only help us if our data was this nice and this exact, which is how we expect the world to be, but the world is never like this. Our measurements have errors, we have outliers in our data, we have data that was misclassified, and so we cannot simply solve an equation to get the variables out of it. What we have to do is to get the variables that best fit the problem that we have at hand. So how do we do this? We go changing the variables and trying to get closer to what we want. So to measure how close we are, we calculate the distance to our goal. We pick up our function, and then we go changing the parameters. So for instance, if we raise the value of b, our line would get up, and our error would be, on average, smaller. And then if we increase w, we would get even closer. And after a few iterations doing this, we could reach a solution that would be acceptable. Okay? So this is best shown with a demo. So I'll try to do this here. So this is real data. It's from a data set that tells us how many miles per gallon can cars do given their horsepower. So points that rank higher are more economic cars, and points that rank to the right are cars that consume, that have more horsepower. So we can see that there's a clear trend over here. And we have this, this really simple function, which has just the W and the B. Actually, here you'll see the values. They're called the kernel and the bias. And I'm going to start a process of finding these parameters. And here my system will try to guess some parameters and try to approximate this function to the data. And eventually, I get a linear function that kind of approximates this data. And I find out that a good value for W and B are these values here. I'm going to run this again just to show you something else, which is down here, I have another chart that shows me how distant am I to my goal. And you can see that as the training progresses, the distance between the points that I predict and the points from the data set gets lower and lower. Okay? So, very well. We ran our first very basic neural network. We trained it, and we got something that kind of predicts the miles per gallon given the horsepower of a car, which is really cool if you ask me. But a linear function would never tell you the difference between a cat and a dog, right? The world is a lot more complex than that. It's not all linear functions. So imagine that our data had this pattern. It's clearly not linear. So we have a linear trend over here, and we have another linear trend over there, but we don't have a single linear trend that can fit correctly the whole data. So what we'd like to have is a single function that could kind of mix these two linear functions together. And there's a function that can help us with this, which is the logistic function. The logistic function has this interesting characteristic that it goes from 0 to 1. And this means that if we multiply something by this function, and we're at the end where it's 0, we're muting that value, because something times 0 is going to be 0. And if we happen to be on the other end, we'll be leaving that value as is. So this function can act as a kind of a switch that goes on or off and enables or disables some other value. So by using this, this function, which is also called the sigmoid because it has this S curve, we could have one function that gives us this trend, another that gives us this other trend, and then use this sigmoid thing to act as a switch and have a single function that's the composition of other linear functions, but this is not a linear function anymore. And this function can now predict nonlinear patterns. Because the sigmoid is actually a curve, it will probably not yield this kind of result with a very visible vertex. It will probably be more of a smooth curve. So let's see this again in action. Let me pick the code of the neural network. And I'm going to change it here on the fly, add another layer that has this sigmoid activation. And I have to comment this one because it's no longer my input. And so if everything runs well and I refresh my example here, what we're going to see is that if I repeat the very same training process, we have the line, it's being fit to the data, and now you can see that it's kind of bending. So it's no longer a linear function. This thing has gained the ability to bend a little bit. I can run the train just a bit longer, And we can see the fitting to the curve becoming better and better. But again, this is essentially multiplying numbers and adding numbers and running them through the sigmoid. So this is actually a very simple process that's going here. And we get the function that very nicely predicts what's the miles per gallon, the car consumption, given the horsepower of a car. So second network that we trained very successfully. So this process of finding the values that live in these W variables and B variables is the training of the network. Okay, so we had our network. It had a function and a sigmoid activation. And if we want to make this more powerful, until the point that it can distinguish between dogs and cats, remember, our final goal, we can just add more and more layers. And the more we add, the more powerful the network becomes and the more fitting to the data it can become. Of course, the training will also become harder. So this is a balance that we have to take. So what's this deep learning thing that I keep hearing about? It's just having a lot of layers. Lots of layers, it's deep learning. Nothing else for this. Okay, so how deep are we getting? This is a task of image classification that's fairly well known as a benchmark for these systems. And originally, we were at 30% error rate. So we want to lower the error rate to the minimum. And the human performance on doing image classification on this data set was about 5%. So this was humans. And these were shallow networks. But at 8 layers, some researchers were able to reduce this to about 11% error rate. To get to 7%, they used 19 layers. To get to 6.7%, they used 22 layers. And to have superhuman performance, they had to use 152 layers. So this is a really deep network, but it gets 3.5% of error on this task, superhuman performance on image classification, which is a really great achievement. So more power, more layers. Okay, so what we've seen so far is that we've reduced this big problem of finding arbitrary functions to the problem of just finding numbers that live on those functions. But I was talking about stuff like classifying images, and images are not numbers. So what we do to solve this is we reduce images to numbers. Actually, here I have an image of numbers. So this is a fairly common data set. It's called the NIST. It's images of handwritten digits. And the task here is usually to guess which digit was drawn by the person. So if we take an image from MNIST, we know that images are just pixels, and pixels have values. And so we can decompose this image in a matrix of numbers. And if we have numbers, then we can use neural nets again. We just flatten this image. We have like a bunch of numbers. Now we can multiply it by a matrix. So before we were using just one number multiplied by another. Now I'm talking matrices. They have lots of numbers inside. But the end result here will be a vector of 10 numbers. And the goal of our network here is to put the highest number on the category that should be the correct category. So here we have 10 categories, one for each number, and we'll want to guess the number 4. Okay? So this will be the right number. And again, why not the demo? So a nice way to see this, to visualize this, is by seeing it happen in real time. So I have this blank canvas here, which means my matrix is full of zeros. And it's being multiplied, a bias is being added. And as I start drawing here, so let me start drawing. Yeah. Wait. Let me refresh this. Okay. Yeah, so as I start drawing here, you see the probabilities go changing as I move my finger. So as I come here, the result of the multiplication is now pointing that this is probably a 7. And if I go down here, it's still a 7, but if I do this detour, this is now adding to the score of number 3 over there, right? Yeah, all right. Now, if I go up, this is just a weird 2 or something. I don't know. This is no real number, actually. And now if I keep going up, you'll see the scores changing. And you see that score for number 8 rising and rising until I get here. So this is really fun to watch, like what distinguishes between, let me try to draw here something like, is this a 4? Yeah, it is. But then if I activate the pixels that are on top, this 4 should become a 9, okay? So again, just matrix multiplication, sigmoids, and suddenly we're recognizing numbers out of images, okay? Right. So what we've seen so far is that we are not finding arbitrary functions, we're finding numbers. And we essentially reduce all the things that are there to numbers. We reduce images to numbers, text to numbers, whatever we have, we reduce to numbers. And a problem of categorizing is reduced to just having a bunch of numbers and getting the highest one. Okay, so let's talk about network architectures. Up until now, I was talking about something that's like a feed-forward network that everything fits in perfectly, functions being fit. I was telling about these matrices, and on this problem of image classification, what will happen is that this W matrix will probably activate the number 4 over there by looking into these regions of the image. And it will probably deactivate number 4 by looking into these areas of the image. So the matrix will be built, it will be trained in such a way that the values for the green areas will be high and the values for the red areas will be negative. Because if I write on those red areas, I'm probably writing number 9 or number 8 and not number 4. This works okay if my number is very centered, but it can become a problem if I do some variations. So it works okay on this case, perhaps not so well on these cases. Perhaps right here the network will fail. So one way of compensating this is by using something called convolutions. So in convolutions, we'll still use matrix multiplication, but we will not process the whole image. We'll just look into a piece of the image, and the result of the convolution will fit just, in this case, in 4 categories. So we'll be trying to classify if this piece is empty, or if it's a vertical line, an horizontal line, or some intersection. And so we see this first piece is empty, then we look to the side and see it's kind of a vertical line, and we keep going through this process, and we keep building this intermediate representation that no longer has pixel values, but has these 4 categories. And now we can have this intermediate representation being also multiplied by a second matrix, and this will give us the final classification. Now, the work that this second matrix has to do isn't that much because it can do simpler stuff like counting the number of intersections that we have. For instance, if we have only 2 intersections, perhaps it's a 4. If we have a single intersection, it should be a 7. So the problem gets a lot easier down the pipeline. And so this is the main point of convolutions. It's that we start with values on pixels that don't tell us much. Then we start extracting features like, is this a line? Is this a circle? And then as we add layers, those layers compose that information and build up new information. So now instead of lines and circles, we'll probably be talking about eyes or windows or doors. And then if we compose, if we see, oh, this has windows and doors, then it's probably a house. And as we add more and more layers, we get less and less points, but we have each point with more and more information, with richer information. So these convolutions are much more resistant to the fact that things can change their position in the image. Okay. And that's why convolution architectures are very often used for image classification. In fact, all the state-of-the-art image classifiers use this strategy of convolutions. Another architecture that's relevant is recurrent networks. And these are used for sequence processing. So let's say I want to classify a sentence as being positive or negative. And I have this sentence over here. I'll probably want to classify this as positive. But I'll have to use the whole context of the whole sentence because the sentence can change the meaning of awesome. So I'll use everything as input and carry on this state up until the very last output. This is because if I change like just one word, the output should also change. So the information that's carried on in the state, it's pretty relevant. So why are these called recurrent networks? Well, because nobody uses this like in this manner. What people do is they leave these outputs being emitted. They start with a blank state. And what we see now is that this box can be the same for the whole sequence. So all these pieces can be reduced to a single piece that is used on the first element. The state is carried on to the second element, and so on, until it finally gets to the end of the sequence and provides the information that we're looking for. And because this block feeds itself with its previous state, that's why it's called a recurrent network. I'm not going to give much more detail on recurrent networks, but I recommend this blog post from Karpati, where he not only explains a lot about sequence processing, but he also has some really cool examples where he uses recurrent networks to feed on text from Shakespeare or Linux kernel source code, and then has the network creating source code. So here's an example of source code produced by a recurrent network. And if you look at this, it really seems like it was taken from the Linux kernel source. The variable names make sense. The comments kind of make sense. The syntax is mostly correct. So this is really impressive if we think that this network doesn't know what syntax is. It doesn't know what the C programming language is. All it knows is that it read some characters and it's outputting some characters. It doesn't even knows words or line endings or what's a comment. But it still can do these things of opening comments, closing comments, matching parentheses. So it's really impressive what these kind of networks can do. Okay, so what we've seen so far is that we have these dense feed-forward networks that are pretty basic, We have convolution that are really cool for images. We have recurrent that are really good for sequences. And now we're going to talk about another data structure that's not a good fit for either of these, which is graphs. So graphs are essentially this structure that's made of nodes connected by edges. And graphs are a very useful structure for representing lots of different types of information, such as physics systems, like how planets interact with each other, molecules, maps, or anything spatial. And they're very interesting to represent code. Why? I mean, code is text, mostly. But for a compiler, code is much more than text. Compilers pick this text and they create these abstract syntax trees of operations. And these trees can be richer in their representation than just the text, because here we can have the notion that all these X's are in fact the same symbol. They are references to the same thing. So the graphs can provide a richer representation about code. And that's why processing code as graphs is much more helpful than processing code as just plain text. So graph networks are a different type of neural network that's made specifically for graphs. How this works is we'll still be processing numbers, and what we'll do is each node of the graph will carry their set of numbers, which will be the information that's being carried. For instance, which variable am I representing, or which code operation am I representing? Now, in order to make this thing more visual, I'll replace the number vectors with Pokemon. I'll describe now the process of how a graph network works. What the graph network does is it feeds each node with information coming from its adjacent nodes, where this feeding process is passing that information through a very small feed-forward network. So what happens is this node in the center, it will feed information from this adjacent node, from this one, and from this other one, okay? And it's not just one node that will be doing this, all nodes will be doing the same, okay? So at the end of a single time step, each node shared information, each node collected information, and all of them became richer in their knowledge of what's on their neighbors. Now, because this happens not with one node, but with every node, at the end of a single time step, the adjacent nodes will have more information. So when we reach like time step number 2, and we repeat this process of absorbing information from adjacent nodes, this center node will already have collected information about everything in the graph. So even if we have very large graphs, about 6 or 8 time steps are enough for most nodes to have any relevant information that they need to fulfill the task that we want them to do. Okay, so just like we had this way of classifying images and by changing the numbers, we'll have the same for the graph networks. Each node will have its set of numbers to represent their data, and after a few time steps, the information contained will change in order to give us the results that we want to obtain. Okay, so if we mark a single node as, hey, I want you to tell me like what variable will be here or what operation will be here, the network can give us that information. So we can start just with some information and in the end obtain what's the right variable for this place. And this is really useful, both for predicting things that are not yet on the code. So we can pick up an abstract syntax tree, put an extra node at the end, and ask the network, what is going to appear here? But this is also useful to predict things that are already on the graph, but that the user might have done wrong. So, for instance, if we have this code, we can just erase that number, that nodes representing that operation, and ask the network to predict which operation should be here. Should be less than, and equals, greater than, and then match that with what the user had written and understand if the user made an error or not. So I was telling you that this was not science fiction. This was already here. And I'm going to give you another example of that, which is Microsoft's IntelliCode in Visual Studio. So this is their system running, and understanding that the predicted variable for that place where the x1 was marked shouldn't be x1, but y1. And so it warns the user, hey, I'm predicting something else here with a high degree of confidence, so perhaps you made a mistake. Perhaps this is a bug. And what's really interesting here is that this bug would never be caught by a simple compiler because all the types check, but the semantics of the thing is incorrect. All right, so this was graph networks. They can do predictions not only on nodes, but also on information carried on edges and on the global graph state. So we can infer, for instance, meaning of a whole graph, like what's this function doing, or what should we name this function? We've already seen usages of graph networks, not only for predicting variables for this code completion and bug detection, but also to predict types. For instance, to help in languages such as JavaScript or Python that don't have types. So there are systems nowadays that use AI-based approaches to predict which types the variables should have and understand, again, if the code is correct or not. And another interesting task here is predicting names. So for instance, if you take obfuscated code, you can predict back the names of the original variables, which is really interesting for checking codes from malware that were obfuscated and reverting it back to understand if it is nasty code or not really. So I talked about stuff that other people were doing, and now I'm going to talk about our personal experience with graph networks. So at OutSystems, we have this development platform where you create logic in a visual manner. And what we've been doing lately is this prototype where instead of you adding the next piece of logic from the toolbar, you just get predictions of what you want to have there. And you can see here in this example that the predictions are highly contextual, so they keep changing as the user adds new nodes. So here we had 3 suggestions, and next we'll have different suggestions, and they will adapt depending on the state that we already have. So when we were doing this system, we were using other AI approaches that were more classic, and we had these accuracies that were kind of okay. So on the top prediction, we were hitting it about 61% of the time we were getting it right. If we considered the top 3, about 88% of the time. And just by changing our models to use graph networks, we had an incredible boost on the performance of the model. So if you remember that chart that I showed with the difference between the error rates in image classification and the amount of layers that you had to add, here we added no layers. We just changed the network architecture, and suddenly our results got a lot better. And we haven't even started tuning the graph network, so we're pretty sure that we'll be able to extract a lot more accuracy from this new architecture. The downside of this is that our input pipeline got a lot more complex because now we're not feeding just matrices of data. We're feeding graphs, which is a more complex structure. And because of that, our training times also got a lot slower, but our prediction times are more or less the same, so it doesn't really affect us much in the end of the day. Another thing that we got from this experience is that although the neural networks ecosystem is quite mature nowadays, we have really robust frameworks like TensorFlow and PyTorch and other stuff. The graph neural network ecosystem, however, it's still at its infancy. So most tools have poor documentation or poor performance. We started using a framework that was built from DeepMind, and 1 month later, we were sending pull requests that could do like 5 times speed up on their code. So there's a lot to improve here. This is still really at its infancy. Now, I have a colleague that only considers using technology if the hype on the technology is really high. And so what's the hype status on graph neural networks? Well, if we look at the comparison with recurrent neural networks, which were all the hype in the last 2 years, we see that this is a thing that is really catching up. So there's recently been a huge increase in the amount of research and papers and use cases for this kind of networks. So we're expecting the whole ecosystem to mature a lot on the next few months or years. So just to sum it up, I think I demonstrated that neural networks are not that hard. They're just things that process numbers, multiplications, and whatnot. But everything can be converted to numbers, so this has a lot of power. More layers mean more power, but architecture matters a lot. And regarding architecture, convolutions for images, recurrent networks for sequences, and obviously graph neural networks for graphs. And because graphs are a very interesting data structure, the graph neural networks open a lot of new possibilities for lots of interesting use cases. And so this is the end. I'm now open to any questions you might have. And I see one hand over there, and another here.
Hi.
Hi.
Thank you for the presentation. It was really cool. I have just a question. Like you said that, like in terms of code, you could use graphs like to predict the type.
Yeah.
Or debug. But you also said that this takes a lot of time, and I don't understand like if this is actually an advantage, because in terms you can, for those kinds of things, you could use like a recurrent neural network of text, like a many-to-one classification task with an LSTM with bidirectional, which would be like way faster and probably way better, given that the current state of art that it's currently available for LSTMs and so forth.
Yeah, so I did say that it takes a lot of time, but it takes a lot of time on training, but in terms of inference, it's neglectable, the difference. So in our experience, you take a lot more to train the models, but when you're actually using them to predict and check if it's buggy or not, the time they take is not really that relevant. So the performance is fairly acceptable. What we understood here is that the LSTMs are all right, but there's a lot of structural information about the code, so the way things relate to each other, that are better represented with graphs. For instance, one thing that might happen in code is that you might declare a variable on the top of a file, then have 2,000 lines of code, and then use that variable. And if you're using a recurrent network to parse text, even if you're parsing tokens, it will be really hard for the recurrent network to remember the declaration of the variable so far off.
Well, nowadays that's not exactly true, because nowadays we have like attention mechanisms, and the LSTM is with bidirectional and so forth. It can take long dependencies. So nowadays, recurrent neural networks take account a lot of long dependencies.
Yes, I know that, but even then, it's very difficult for the network to learn that it should conserve that information for so long. The thing with graph networks is that because you have a direct edge between the declaration and the usage, then it's just over there. You can think of a graph network as a recurrent network where instead of going from the top token to the bottom one, you go through the edges. And so this gives it a higher richness on the understanding the code pattern.
Understand now, full explanation. Thank you.
Okay. Here.
Hello, thank you for your presentation. How do you train these kind of networks? So in the feed-forward, you do backpropagation. How does it work here?
Okay, so here what happens is we have to also convert our graph representation into matrices. And what we end up having is a matrix that represents all the node data, one that represents all the edge data, and then we have some auxiliary matrices that represent how nodes and edges are related. And then instead of doing direct multiplications, we have to use kind of a selective multiplication where we only apply things to nodes that are connected, not to any node. So it's a trickier process, but you can almost think of it as a convolution that instead of looking into the local space, looks only at the connected space. Okay?
Thank you.
Hi, thank you. Great presentation. My question is, in the end, you end up with a trained neural network that will make the predictions for everyone's code, really. So first question is, it doesn't adapt to every little project you have. So say you have three clients, and they will have, all of them will have the same predictions, nevertheless what the project is. And second question, sorry, is how did you prepare your training set? Because this is a crucial part of training a neural network. It's highly dependent on how good your training set is. So how did you tackle that?
Okay, so those are very interesting questions, and they're actually still open-ended in this problem of using source code to train. So you have a lot of text written in books and Wikipedia and everything that you can train on, but source code is a lot more limited in its availability. I mean, you can train your network on the whole kernel source code, but there's only 2 or 3 kernels available that you can do your training on. So the training set is reduced in that matter. You have to look into various small projects, and you have this issue of how can I be sure that I'm not learning bad patterns. So if everyone's making the same bug, perhaps my network will learn to suggest a bug, which is really a problem. And so what we're kind of hoping here is that the bugs eventually get fixed while the good patterns eventually stay. And so we're hoping that the bugs get averaged out in the training, but the good patterns stay and are reinforced throughout learning. But this is a hope. This hasn't yet been proven, and it's something that we're still researching. So how can we be sure that the quality of our suggestions is valid? And also, if different customers of ours or different projects have different coding styles, how could I adapt my network to their specific coding style. So we know that the guys at Microsoft now have this feature where they can train the models specifically on a project's code, so they can use information from other projects, but then do a fine-tuning over just one project's code, and to learn patterns that are specific to that project. So they're researching on that. I think they already have some prototypes running. I don't know yet how good are the results, but it's certainly something that we're still researching, and it's still an open-ended question, unfortunately. Yeah.
Thank you.
One more.
Hi, thanks for the presentation. One question is, I still see this as a supervised problem, right? So I would like to understand the examples that you provide to the graph network. How do you decide that it's a good code and bad code, like a bug?
Yeah.
How do you take care about data provenance, for example? Is it from the OutSystems code base that you provided and teach the algorithm, or how do you do it?
I'm sorry, I just didn't understand the last
It's
part.
like how do you do this kind of examples creation to feed the graph neural networks so that it learns? How do you create the examples?
So we used a lot of patterns that we collected from projects that our team of experts developed. So we kind of hope that their code makes sense and is correct. So that was our main source of data. Now, you were also talking about being this kind of a supervised problem. How do we get this to a goal that makes sense? So, right, what's our supervision? So what we did was we picked up slices of code and we simulated a construction of the code. So we start with, we pick up a flow and then we break it apart. So just the first node, just the two first nodes, then another, and the task is always predicting the next one. And then we can have branching, then we can cut some parts in the middle and try to predict that middle part. So this was the kind of things that we have been doing. We have some other ideas that we haven't explored yet on other different tasks that could also give us useful information, but we haven't yet experimented with them.
Thanks.
Okay.
Hi, Miguel.
Hi.
I was just curious what you think about this kind of technology to be used. Do you see this as used as an helper or an assistant of someone that is trying to create something in this type of platform, or do you see that this can be used as an autonomous agent that is writing code for itself, or more like a tool that the developer uses to help him?
Okay, so I think the whole gradient is valid. So this can be used for helping an expert developer with finding some bugs on its code. It can be used to help a novice into getting to the right direction. And there's also another interesting angle here, which is most code synthesis research is not done over artificial intelligence or machine learning methods, but it's done over theorem provers and constraint solving, so more formal methods. Now, formal methods have this problem, which is they have a big search space, and so they take forever. And these approaches can be melded together so that the AI systems can just provide directions so for the constraint solver to reduce the search space that it's solving. You usually want constraint solvers for code generation to make sure that the code is exact and satisfies a bunch of norms that make it okay. Okay. So I think we don't have time for any more questions, but I'll be around. You can ask me whatever you want later on. Okay, thank you.